In this example, we're working with the law of Gay-Lussac. This law says that in a chemical equation, as long as all the substances with which I'm working are gases, then the coefficients in the chemical equation not only relate the number of moles of each substance, but they also relate the number of liters of each substance. It only applies to the substances if they are gases, but it can be very useful, as this example will demonstrate. The problem asks, if a car burns 12 liters of octane, C8H18, how many liters of carbon dioxide are produced? Now, we aren't given a chemical equation, but we know the chemical equation for combustion. We add oxygen, we make carbon dioxide and water. Now, sometimes you don't know the phases in a chemical reaction. In this case, you do. The problem tells you that the C8H18 is gaseous, and you know that in combustion, the oxygen, the carbon dioxide, and the water are all gaseous as well. So this is a great equation for the law of Gay-Lussac, because all of the substances are gases. Now, of course, before we do stoichiometry, we have to balance the chemical equation. I'm going to assume you can do that. So here's the balanced chemical equation. Now let's do the stoichiometry. Since the substances we're interested in, C8H18 and carbon dioxide, are both gases, then the coefficients in the chemical equation not only relate the number of moles of the substances to one another, but also the number of liters. So, the coefficients are 2 for C8H18 and 16 for CO2. Alright, that means that 2 moles of C8H18 equals 16 moles of CO2. But, since both of these substances are gases, it also means that 2 liters of C8H18 equals 16 liters of CO2. Now that I have a conversion relationship, I can convert. I've got 12 liters of C8H18. I put that over 1, and then I multiply by 1. But the expression for 1 comes from the conversion relationship. I need to get rid of liters of C8H18, so those are going to have to go on the bottom of the fraction so that they cancel. And that leaves liters of CO2 on the top, which is what I wanted to solve for. Now when I multiply these fractions, liters of C8H18 cancel, and when I plug through the math, I get 96 liters of CO2. The significant figures are correct. The 16 and the 2 are exact. They come from the chemical equation. So the only number with significant figures to worry about is 12. It has 2 significant figures, so my answer can have 2. Now understand that the only reason this worked is because the substances we were interested in were gases. Had one of them been a solid or a liquid, I couldn't have done this. The coefficients in the chemical equation only relate liters when the substances you're interested in are all gases. That's the law of Gay-Lussac.